Okay, here we go. Ladies and gentlemen, we are doing more with synthetic division and factoring and zeros. Yay! Okay, so today we're talking about the rational zeros theorem, which I have to say, you know, like, this is the first year I've taught using this material, and so every year I go through and I like edit and refine stuff to make it a little faster, a little less monotonous. This is one of those things where I'm like, why do we still teach this? Because we have calculators, you know. But it is kind of handy, and once upon a time we didn't have calculators, and at some point there will be an EMP that will knock out all the technology after 1978, and nothing will work anymore. I guarantee it. An EMP, an electromagnetic pulse. All right, I guarantee it. I am not a conspiracy theorist, but of all the things, our electric grid is going to get hit, and there's going to be an EMP, which can happen from solar flares, and that it'll happen. So, there are a few things I believe. I don't believe that because that doesn't make sense. All right. So today we are talking about the rational zero theorem, and so we want to recall that a polynomial function. A polynomial is a nice smooth curve graphically. They have many different looks to them, but they're like stretchy S's or W's sort of shapes. A polynomial function of degree n can have at most n real zeros, meaning there are n x-intercepts. Because that's what a zero is. It's where the graph crosses the x-axis. That is where the y value has a value of 0. All right? We have an x value, but the y value is 0, and that's why they're called zeros. Now, those real zeros can be rational or irrational. Okay? Rational, what is a rational thing? Rational, fractional. Yeah, rational, fractional. Rational fractional, it's a zero that can be written as a fraction. It's a nice number. It's maybe a 2, or maybe it's a 2/5, or maybe it's a negative 1/4. Okay, those are nice numbers. But irrational is something like radical 2 or radical 17. It's something that is some sort of really crazy thing. So radical 17 is this crazy decimal 4.123 yada yada yada. That's totally irrational. That decimal goes on forever. It's crazy. It doesn't repeat. It is totally weird. So we call that crazy irrational. All right, so rational zeros are those that can be written in the form of a fraction where we have p over q. That's the letters we're going to use today, p over q. So rational fractional, I love to say that. Now, it turns out that the rational zero theorem can be used to determine all possible rational zeros of a polynomial function. And if I have some crazy polynomial, this is its weird-looking form, if a polynomial has integer coefficients, what are integers? Positive or negative whole numbers. So negative 3, negative 2, negative 1, 0, 1, 2, 3, So integers are the positive and negative whole numbers. Okay. So if there are integer coefficients, so if we have nice, pretty integer coefficients, numbers in front, then every single rational zero is of the following form, where p are the factors of the constant term. The constant term is a sub 0. That is the very last thing. whatever the last number is, it is the factors of the constant term over the factors of the leading coefficient, which is a sub n. It is the first coefficient. So it's the last coefficient over the first coefficient and all the factors and all the combinations of that, plus or minus. What does that mean? That is very long and drawn out. So we want to just create a little list of the possible rational zeros, which is kind of interesting. So this right here is the 2. That is our P. And the Q, what number is in front of x cubed there? 1. It is a 1 right there. So that is the Q. The P is the last. It's the constant. The Q is the coefficient that leads. And what we want is we just have to list all the possible rational zeros, which would be all the factors of 2 over all the factors of 1. Which, this is a stupid one. I don't know why I started with this one. What are the factors of 2? 1 and 2, and that's it. What are the factors of 1? 1. And so what this means is we could have, plus or minus, we could have 1 over 1, 1 over 1, or 2 over 1, which is really just plus or minus 1 over 2, or 1 and 2, rather. Well, let's try something a little bit harder. Number 4. Our constant term is 16, and our leading coefficient is 3. And so to generate a list, we want all the factors of 16. What are all the factors of 16? 1, 2, 4, 8, 16. How do I know that? Yeah, because we know our factors, right? 1 times 16 is 16. 8 times 2 is 16. 4 times 4 is 16. All right, there we go. And then we want our factors of 3. What are the factors of 3? 1 and 3. And that's it. Those are the only options we've got there. So now what we have to do is generate this possible list. Well, I'm just going to take 1 over everything over the 1. So 1 over 1, 2 over 1, 4 over 1, 8 over 1, 16 over 1, everything over 3. So then 1 over 3, 2 over 3, 4 over 3, 8 over 3, and 16 over 3. These are all the possibilities that we could have, which is kind of crazy. So at least one of these might be one of our roots on this polynomial. And so that's the list, positive or negative, all of those possibilities. Does that make sense to you? Pretty easy to generate that list, right? Not too shabby? Okay, great. Let's turn the page. I don't really care about that. So here's what I really care about. We want to find the rational zeros, actually. And so we have a nice little process for finding them. We want to list all the possible rational zeros using our little rational root list. Okay, so we're going to generate a nice big list. But then we're going to test using synthetic division and our calculators because they're going to help us out here because I'm not totally lame. Okay, and then when you find a zero that works, we are going to factor the polynomial completely and find the zeros. So we are going to use our calculators to help, but we can still list all these things. So first, I'm going to generate my little list. I have, I did not want to do this one. Let's not do this one. I don't want to do the first one. I wanted to do number 8. Let's look at number 8. Number 8, we're going to generate our little list here. My constant term is 20, and my leading coefficient is 1. So I want to generate my list. What are all my factors of 20? 1, 2, 4, 5, 10, and 20. Good. All right. And then our coefficient of 1. So that's it. Those are our factors, 1 over 1, 2 over 1, which is really just 1, 2, 4, 5, 10, and 20, plus or minus. So these are all the possible zeros. Okay, we listed them. We did our job. Now you know the rational root theorem. Let's go ahead and use our calculator because we have a calculator. So x to the third power minus 21x plus 20. We're going to go ahead and do a Zoom standard. And all I need is 1, ladies and gentlemen. And again, can you cheat? Do you know the zeros? We have calculators, okay? But I need you to do the math, all right? So we need to pick 1. So what is one of our zeros here? 1. Hey, that's a great one. All right. So we're going to use 1 in synthetic division. And let's see here. If I use synthetic division, what do we have to do across the top here? 1, 0, negative 21, and 20. Very good. You filled in your missing term. That was important. All right. So we're going to go ahead and bring down the 1 and then multiply and combine. So 1 times 1 is 1. Combine, we get 1. Multiply, we get 1. Combine, we get negative 20. Multiply, we get negative 20. And we get, lo and behold, a remainder 0. Remainder 0 means that it went in nice and evenly. So I can rewrite my function, my f of x, my polynomial, as if x equals 1 is the 0. What's the bubble that it came from? X minus 1. So if x equals 1 is the 0, what bubble did it come from? It came from x minus 1. You just have to sort of slide the 1 back to the other side. And what is the quotient? What's the leftover bit here? X squared plus 1x minus 20. Good. And from there we can double bubble. We have x times x is x squared, and what times what is negative 20? Positive 5 and negative 4. And so here is our completely factored polynomial. And that's important. Totally factored. And from here, then it's really easy to see the zeros. What are the zeros? 1, negative 5, and 4. And, of course, did we know that already? Yeah. So please, ladies and gentlemen, do the work because it's amazing how the work connects. All right? Just going from the polynomial and then verifying it with the algebra, it's really pretty amazing.
So it can work with any one of the zeros, but it's just to find all the zeros.
Yeah, and so this is the possible list of all of them, potential zeros. And we just have to pick one. Let's do, I think, one that I wanted to do. Turn the page. Let's do 2 more. I'll do 12 and 13. We got time. So 12 and 13. Number 12, we have our P and our Q. And so our plus or minus list of potentials here. What are all the factors of P? 1, 2, 5, and 10. And then our factors of Q are 1 and 3. So our potential list, we would have 1 over 1, 2 over 1, 5 over 1, and 10 over 1. But also 1/3, 2/3, 5/3, and 10/3. So these are all the possible rational roots. Does anyone have any questions on how I got those? You good? Okay. So now what are we going to do? We're going to use our calculator to help us out because otherwise we're just going to sit there and plug something in until you get a remainder 0. Like that's, you just have to do synthetic over and over. So what's amazing, what I find amazing is that they figured this out in the 15th century. They didn't have calculators to help them out, right? And so they had to go through and they figured out synthetic division. That's pretty amazing. All we did was recognize patterns. It's pretty cool. But they figured all this stuff out without calculators. And I know you're like, but we have a calculator, so why bother? And you're right. It can be kind of, annoying. But I think it's still pretty cool, and it's a good thing to know. Because like I said before, there will be an EMP, and this thing's going to die. And you're going to need to know how to do it still. Okay. All right. So when I graph this thing, all right, -2? Let's try -2. So we're going to try -2. We're hoping for a 0 at the end there. Let's see, 3x cubed, -8, -33, and -10. All right. -6, -14, 28, -5, +10. Remainder 0. Okay, so we got a remainder of 0, which is very, very good. So I can rewrite my function f of x as, if x equals -2 is the 0, what bubble did it come from? X plus 2. Again, you got to change the sign, all right. And then what is our quotient? 3x squared minus 14x minus 5. Good. And from there, we should be able to double bubble more. And I definitely think we can, because 3 times 5 is 15. That's 1 away. So I want to keep 3x times x, and I want to multiply with that 5. So -15 and a positive. Did I do that right? How do you know if you did that right? Check the O and the I. So we have a -15x and a positive 1x, and that gets me that middle term, that -14. All right. So I know I did it right. Okay, so there is my totally factored polynomial right there, completely factored. And then I can list the zeros really easily. X equals -2, -1/3, and +5. All right. Not too shabby. All right, number 13. We got to do something called piggyback. It's not really called that. I call it that. Piggyback synthetic. You'll notice, because this is a x to the 4th power. So it's a higher degree. It's going to be a little bit harder. But let's go ahead and create our little list here of P over Q, which is 1. What are our factors of 30?
1, 2, 3, 5, 6, 7, 8, 9.
Good. 1, 2, 3, 5, 6, 10, 15, and 30. Very good. All right, so there are our potentials. And again, I'm going to go and plug them in. So we have x to the 4th plus x to the 3rd minus 31 x squared minus 61x minus, and of course the biggest problem with this is typing wrong. Ooh, interesting. What do you see in this polynomial? Multiplicity 2. Yeah, we're bouncing off this 0. Yeah, multiplicity 2. Love that. Okay, so looking at our graph, we can see a potential here. What potential 0 do you want to try? What do you want to do? -4 or 5? -5. 1, 2, 3, 4, 5. Yeah, -4 is not on our list, but -5 is. Okay, great. So 1, 1, -31, -61, -30. All right. So I'm going to do synthetic division. 1, -5. So I did synthetic division. I got my remainder of 0, which is great. But I'm thinking to myself, hey, when I write this out, this becomes x to the third 4x cubed minus 11x or cubed squared, minus 11x minus 6, right? And I can't double bubble that. So we got to do it again. So I'm going to go back to my graph and pick another. So this is where I call it piggyback. What I'm going to do is just piggyback right off of our little quotient here and pick another 0. We've already used -5. What else can I use? I could. Can I use -1? Yeah, I just want to use -1. And so now I'm just going to piggyback right off my coefficients right here. And so I'm going to bring down my 1 again. And that's going to be -1, -5, 5, -6, +6, 0. And I get another 0 there. And so now that brings it down to a manageable level. So I can rewrite my function as, if the 0 was -5, what bubble did it come from? X plus 5. We had x equals -1. What bubble did that come from? X plus 1. And then now here's our little leftover quotient. How do I write that in a polynomial form? 1x squared? Good. And again, what's happening here is we started with a degree 4. And when we're dividing through with this -5, we're dividing out an x. So x to the 4th, divide out an x, that gives us a cubic. But then we divided another x away, and so now we're down to an x squared. And then from there, we can double bubble that pink stuff one more time. How does that double bubble? -6 plus 1. Yeah, good. X minus 6 times x plus 1. All right, we had the x plus 5 and the x plus 1. All right, so this is our polynomial fully factored. All linear factors, which is great. And then what are the zeros? -5, -1, and 6. Very good. And you don't need to write the -1 2 times. Once is enough. All right, ladies and gentlemen, do you have questions for me? All right, cool. No, it's Delta Math.